So today we'll be looking into the Hooke's law graphical presentation. How could we understand the functionality of Hooke's law, how it is getting proportional, how it is not getting proportional, in what situation Hooke's law is not implementable. So these all factors we'll cover today's video. So we're very first to understand Hooke's law, what you need to actually consider is that consider an object. Just suppose for a while this is a object which is having somehow a mass, area, length, width, each and every factor is actually working on this object. Now, in a situation, we are actually applying external force to this object, or just suppose for a while to make it more understandable, let's say that this is a person A, who is pulling this object by a thread. He or she have tied up this object and she started moving in that side. Now what will happen? What will gradually happen, that this is the actual initial stage, and after moving on, its actual shape will get extended because of that external force. The more that person will apply force, the more deform it will get, right? So what we could say here, that because of the F that this man is applying on this object, there is sort of extension that is taking place. The more the F, the more the extension. The less the F, the less the extension. This is the basic concept of Hooke's law, where we indeed actually term this X by, or actually alternate this E by X. Well, it's totally up to you. You can use this terminology as well, E. That's also fine. So here, the thing that will explain that how much an object can be stretched, how much extension can an object can have, this thing is explained by one of the most important term, that is a spring constant. Spring constant, that is often denoted by K. So F is actually equal to K times the E. The K is actually Newton per meter, and E is of course meter, since it's denoting as the change in distance, right? So it will be M. Howsoever, F is actually equal to Kx, and K is again, now the more the K, the more the force is required. The more the force, the more the K, and less extension. Now what I meant to say, just suppose for a while we are having this K object which can be extended till 5 meter. Okay. Now we are applying force to it. This is at the situation where it is of 1 centimeter. We are applying force, it will get extended. Again, it will become of 2 or maybe 3 meters, right? But again, if in a situation it is exceeding the limit of 5 meters, so what will happen? There will be less extension. There will be another feature that we often known as non-Hooke's law implementation. Now here the basic concept that we got is that K is directly proportional to F, where the more the K, that means the more an object can actually rely on the force, the more the force we can implement. The more the K an object will have, the less the extension it will have, or the less, what we can say, the more brittle it would be. Now let's understand this concept by a graph. Here we know that in a basic graphic or basic maths, whenever we are writing something on the x-axis, we have to take care of this thing, that x-axis is a variable that is independent. That means because of x there is production of y. This thing we need to take care, and by denoting this thing or by looking into this factor, we would get a term that is force. On the x-axis we'll keep force, and on the y-axis we'll keep a term known as E or extension. Okay, let's zoom out. First, suppose we are taking an object that is A. Now we are making graph of this A object. If we are applying force, just suppose till 1 Newton, right? So 1 meter would be the extension that it will get. Again, it will create an sort of a straight line, or I think I should use an actual straight line to showcase this thing. Let's say this is a line that we got. Now this is a straight line that is being created in terms of, this is a proper slope, so it should be on the 45-degree, right? Now this is a proper slope of the A that we got, that actually denotes us that this object is showing us a perfect combination of extension and force, where both of the factors are working simultaneously. If you're actually exerting 1 Newton force, so it's creating 1 Newton of the charge, or 1 Newton of the extension. Howsoever, if we'll take out K, suppose in this situation, let's consider we are applying force 2 Newton and we are having extension of 2 meter. So the K is constant for this object, that is 1. So K is always constant. So keep this thing as under consideration. Howsoever, if we'll exceed this point, just suppose this is, we are calling this point as B and this point as A. Okay, let me reduce the weight of my pen. After this extension, there will be a curve in the situation. Now B is basically the limit of proportionality. Just suppose for a while you are taking an object that is rubber. So you can actually exceed, or you can actually stress rubber until a situation it's not getting breakdown or it's not getting broken. Now if you are taking a spring, you often have seen a situation where, if we are, just suppose for a while this is a spring which is actually a new spring, we are stretching it, and because of our stretch it's getting into this point, right? Now if we are leaving it, so it's getting back to its original place. Again we are stretching it, and now we are stretching it a bit harder. Now this spring is getting back to the situation, but if we are having this extension as 3 meters, so it's again getting back, its actual length is 0. So it's again getting back, but with some permanent stress applied on it. This is called a situation where there isn't any Hooke's law that can be applied. So from the point of the limit of proportionality, there will be no Hooke's law that can be applied. It can only be applied in a situation or within a situation of proportionality. Okay, I hope that this concept is clear to you all, and thank you so much for watching the video.